Tonight I'm going to take you on a journey through one of the most remarkable stories in all of human history. It is the story of how we learned to see farther. How curiosity and glass and starlight and the patience of centuries slowly opened the universe to us. It is the story of the telescope. Let your pillow hold your head. Let your bed hold your body. We have all the time in the world. And before the naked eye had any understanding of what it was truly seeing, there was simply the darkness. Imagine a night from a very long time ago, 50,000 years ago perhaps, 100,000. The campfire has burned low. The last orange embers pulse with a slow, sleepy rhythm, like a heartbeat, like your heartbeat now, steady and calm. A person lies on their back on the open ground. The earth beneath them is cool and firm and real. The sky above them is vast and staggering. There are no electric lights. There is no city glow, no orange haze above distant buildings, no headlights sweeping across bedroom walls. There is only the sky, and the sky is completely, incomprehensibly full. Stars beyond counting, thousands upon thousands of them, so dense in places that they blur together into a pale river of light, a smear of brightness arching from one horizon to the other. What we would come, much later, to call the Milky Way. The person looking up at this sky does not yet know what stars are. They do not know about nuclear fusion, or light years, or the expanding universe, or gravitational lensing, or any of the magnificent and intricate machinery that hides behind the beauty. They only know that the sky is there, constant, breathtaking, and something in them, something deep and animal and very, very old, wants to understand it. That wanting is where our story begins. Not with lenses or mirrors or mathematics, not with workshops or universities or scientific societies, but with a human being lying on their back, in the dark, looking up and feeling, somewhere beneath the wonder, the first quiet stirring of a question. What is up there? For tens of thousands of years, that question lived only in the mind and the eye. And yet, with nothing more than those two instruments, thought and vision, ancient peoples achieved extraordinary things. Let your body relax a little more as we drift back in time, back to the great river valleys and the desert plains where the first great civilizations were quietly, methodically, turning observation into knowledge. Along the banks of the Euphrates River, in a land we now call Iraq, the Babylonians watched the sky with a dedication and a patience that is, even now, difficult to fully comprehend. Night after night, for generation after generation, Babylonian priests and astronomers stood on the flat rooftops of their ziggurats, those great stepped temples that rose like mountains from the flat Mesopotamian plain. And they recorded what they saw. They had no telescopes. They had no clocks in the modern sense. They had clay tablets and sharpened reeds and an extraordinary capacity for careful attention. And over centuries, those records accumulated into something remarkable, the ability to predict. The Babylonians could predict the rising and setting of the planets. They understood the cyclical nature of eclipses, using an 18-year cycle, which they called the Saros, to know, well in advance, when the moon's shadow would darken the sun. Think about that for a moment. Without a single piece of glass, without any optical instrument whatsoever, without any understanding of the physical mechanics behind what they observed, these people could look at their records, trace the patterns, and tell you, in 18 years, 11 days, and 8 hours, there will be an eclipse. The power of patient observation, the power of watching, and writing, and waiting, and watching again. Far to the west, in the sun-bright lands of Egypt, other eyes were also turned skyward. The Egyptians oriented their greatest monuments, the pyramids of Giza, with astonishing astronomical precision. The three great pyramids of Khufu, Khafre, and Menkaure have been proposed by some researchers to mirror the arrangement of the three stars of Orion's belt, a popular idea known as the Orion correlation theory. It is worth noting gently that this claim remains contested among mainstream Egyptologists and archaeoastronomers, who point to significant problems with the alignment when examined rigorously. But what is widely accepted and genuinely remarkable is what follows. The shaft inside the Great Pyramid, pointing upward and northward through thousands of tons of limestone, is aimed with an accuracy that confounds modern architects at the northern pole of the sky, at the circumpolar stars that never rise, never set, but simply turn in slow and stately circles, all night, every night, around the unmoving point at the axis of the heavens. Eternity made visible. That is what the ancient Egyptians saw when they looked north at the night sky, and they built their eternity in stone to match it. Now let your breathing slow a little more. There's no hurry. Let each breath come and go at its own gentle pace. In ancient Greece, the sky became not just an object of observation, but an object of thought, of reasoning. The Greeks brought something new to astronomy, the desire to understand not just what the sky did, but why. Aristarchus of Samos, in the 3rd century BC, proposed something that would not be widely accepted for nearly 2,000 years, that the Earth moves around the Sun, not the reverse. That our world is not the still center of all things, but a traveler, a wanderer, orbiting the great burning star at the heart of our system. He was right, and the world was largely not ready to hear it. Eratosthenes, also in the 3rd century BC, did something even more concrete, and perhaps even more astonishing. He measured the circumference of the Earth, using a stick planted upright in Alexandria, and the knowledge that at Syene, a city far to the south, the sun shone directly down a deep well at noon on the summer solstice, casting no shadow at all. Eratosthenes calculated the circumference of our planet to within a remarkably small margin of the true value. No satellite, no GPS, no telescope, only careful thought, patient measurement, and the profound willingness to ask, if a shadow falls at one angle here, yet casts no shadow at all somewhere else at the very same moment, what does that tell me about the shape of the world? And Hipparchus, in the 2nd century BC, created the first comprehensive star catalogue. He mapped roughly 850 stars, assigning each a brightness on a scale of 1 to 6, a system we still use today in a refined form, called apparent magnitude. He also discovered, by comparing his own observations with records left by earlier Babylonian astronomers, that the position of the stars relative to the equinoxes very, very slowly shifts over time. A great celestial drift that takes approximately 26,000 years to complete one full cycle. We call this precession, the slow wobble of the Earth's axis, like the wobble of a spinning top as it winds down. Hipparchus discovered it without any instrument more complex than a sighting rod and a divided circle. Discovered it because he had access to Babylonian records from centuries before and was paying close enough attention to notice that something had moved. Patience, attention, records passed down through time. These were the first telescopes, not of glass and metal, but of the mind. Meanwhile, in China, court astronomers were keeping their own meticulous records that would later prove invaluable to modern science. Chinese astronomers documented comets, sunspots seen with the naked eye through morning mist, novas, stars that suddenly brightened and then faded. In 1054 C, Chinese and Japanese astronomers observed a guest star, a star that appeared where none had been before, blazed brilliantly for weeks, and then slowly dimmed away. We know now that what they saw was the death of a massive star, a supernova, and the cloud of gas and dust that explosion left behind, still expanding outward through space today, is one of the most famous objects in the night sky. We call it the Crab Nebula, and we know it is there because people, careful, quiet, dedicated people, were watching the sky in 1054, and they wrote down what they saw. Let your body sink a little deeper now. Feel the weight of your limbs, the warmth of the blanket, the perfect stillness of the room around you. We move now to a different part of the world, to the flickering oil lamp glow of medieval workshops and libraries and courtyards, where a new kind of knowledge was being carefully, lovingly assembled. Between roughly the 8th and the 13th centuries CE, the Islamic world was experiencing what historians call a golden age of science and scholarship. In the great cities of Baghdad, Cairo, and Cordoba, in libraries and observatories and workshops across a vast arc of the world from Spain to Persia, scholars were doing something remarkable. They were preserving the knowledge of Greece and Rome, translating ancient texts, and then they were pushing further, questioning, experimenting, adding to what they had inherited. Ibn al-Haytham, known in the West as Al-Hazen, was perhaps the most important optical scientist who ever lived. Working in Cairo in the early 11th century, he wrote a monumental text called Kitb al-Manir, the Book of Optics, that would shape the science of light and vision for the next 6 centuries. Al-Hazen made a fundamental conceptual breakthrough. Before him, there were essentially 2 competing theories of vision. One said the eye sends out rays that touch what it sees, like fingers reaching out from the body. The other said that objects send out images that enter the eye. Al-Hazen studied this problem carefully. He designed experiments. He gave the first clear scientific explanation of the camera obscura, a darkened room or box with a small hole in one side, demonstrating geometrically how light from outside projected an inverted image on the opposite wall. Earlier thinkers, including the Chinese philosopher Mozi and Aristotle, had noticed the phenomenon. But Al-Hazen was the first to explain precisely why and how it worked. He concluded, correctly, that vision works because light from external objects enters the eye, not because the eye reaches out. The eye is a receiver, not a projector. This seems simple now, but for the history of optics, and thus for the history of the telescope, it was everything. Al-Hazen also studied the refraction of light, the way light bends when it passes from one medium into another, from air into water or glass. He measured angles of refraction. He examined lenses. He wrote about the magnifying properties of curved glass surfaces. He did not build a telescope, but he laid almost every conceptual brick that would eventually support one. Now, glass itself had been made for thousands of years. The ancient Egyptians made it. The Romans made extraordinary glass, thin, clear, beautiful. But for most of history, glass was used for vessels and decoration, not for optics. The transformative development came gradually, in the workshops of medieval Europe. By the late 13th century, glassmakers in Venice and along the Italian coast had developed techniques for making glass pure enough and regular enough to be ground into lenses. And lenses, first in the form of reading stones, smooth rounded pieces of glass or crystal placed on text to enlarge the letters, began to appear among scholars and scribes. Then came spectacles. The first wearable eyeglasses appear in historical records around 1280 to 1290 CE in northern Italy. The inventor's identity remains uncertain, a mystery of history, but their impact was immediate and profound. Imagine being a scholar or a craftsman in your 40s or 50s, Your eyes no longer able to bring small letters or fine detail into focus, a condition called presbyopia, the almost universal hardening of the eye's lens with age. And then imagine holding a piece of curved glass before your eye and having the world snap back into clarity. The effect must have felt like a miracle. Spectacle making spread quickly from Italy to the Netherlands, to Germany, to England. By the 14th and 15th centuries, lenses were being ground and polished by skilled craftsmen in workshops across Europe. The techniques were refined, the glass was improved, and the understanding of how curved surfaces bent and focused light was slowly accumulating. Roger Bacon, the English friar and philosopher writing in the 13th century, had speculated, with remarkable prescience, that lenses might be arranged in such a way that distant objects could be made to appear near. He described, in vague but suggestive language, the possibility of seeing the moon and stars as if they were very close. He was imagining a telescope. He did not build one, but he was imagining it. And so the pieces accumulated, slowly, like snowflakes settling on a quiet field. The knowledge of how light bends, the skill to grind glass into precise curves, the understanding that a curved surface magnifies, and the human longing, ancient, unquenchable, to see what was too far to see, all of it gathering, quietly, over centuries, waiting. The year is 1608. The place is Middelburg, a small, prosperous city in the province of Zeeland, in the Dutch Republic. Middelburg is a city built on trade. Its harbor is busy. Its streets smell of the sea. The Dutch Republic in 1608 is a mercantile powerhouse, its ships crisscrossing the globe, its workshops producing goods of extraordinary quality, fine cloth, precision instruments, painted panels of oil and pigment that are just beginning to astonish the world. In a workshop near the market square, a spectacle maker named Hans Lippershey is at his bench. We don't know a great deal about Hans Lippershey as a person. He was born in Germany, in Wesel, possibly around 1570. He moved to Middelburg, probably in the 1590s, and established himself as a maker of eyeglasses, a respected trade in this wealthy, literate city. There is a story, charming, perhaps apocryphal, but persistent, that the telescope was discovered by children. The children, so the story goes, were playing in Lippershey's workshop. Children always find a way into interesting spaces, and they discovered, as children discover things, by accident, by play, by the irresistible urge to look through things and around things and over things, that when you held two lenses up, one in front of the other, and looked through both of them at once, the distant weather vane on the church tower appeared close. Whether or not this particular story is true, something like this realization occurred in or around Lippershey's workshop, sometime in the first years of the 17th century. Two lenses, a concave one and a convex one that spread the light and one that gathered it. Held in the right relationship to each other, the far became near. On October 2nd, 1608, Hans Lippershey submitted a patent application to the government of the Dutch Republic for a device by means of which all things at a great distance can be seen as if they were nearby. His instrument, a tube of about 35 centimeters, with a convex objective lens at the far end and a concave eyepiece at the near end, could magnify objects approximately 3 times. 3 times. It seems modest, doesn't it? And yet, the Dutch government immediately recognized the military implications. A general who could see the enemy's movements 3 times more clearly than the enemy could see his, the advantage was enormous. They ordered Lippershey to make binocular versions, for use with both eyes. They paid him generously for his work. They also denied his patent application, because within weeks of his submission, other craftsmen, Jacob Metius of Alkmaar and possibly Zacharias Janssen of Middelburg, had presented similar devices. The idea, it seemed, was in the air. Multiple people were arriving at the same discovery, independently, within the same small window of time. This happens in the history of science and invention. Ideas mature slowly in the collective soil of accumulated knowledge, and then, when the conditions are right, they spring up in several places at once, like the first flowers of an early spring. News of the Dutch looker, sometimes called a spyglass, sometimes a perspective glass, spread across Europe with remarkable speed. Within months, word had reached Paris, Prague, London, Rome, and the city-states of northern Italy. Among the people who heard the news, in Padua, in the Venetian Republic, was a 45-year-old mathematician and natural philosopher who had been waiting his whole intellectual life for something very much like this. His name was Galileo. Take a slow breath with me, in and out. Feel your body growing heavier, the muscles of your face softening, your eyelids settling. There is nowhere to be but here, in this quiet place. Listening, Galileo Galilei was born in Pisa in 1564, the same year, as it happens, that William Shakespeare was born in Stratford-upon-Avon. There is something poetically resonant about that coincidence, as if the universe was arranging, in that one year, for extraordinary things to be made of human observation, one through a lens, one through language. By 1608, Galileo was a professor at the University of Padua, one of the most celebrated universities in Europe. He was known for his work in mechanics, the study of motion, for his dismantling of Aristotelian physics, for a mind that combined mathematical rigor with practical ingenuity. When word of the Dutch telescope reached him in the spring or summer of 1609, Galileo did not simply order one from the Netherlands. He sat down, thought carefully about what he knew of optics, and built his own. His first attempt magnified about 8 or 9 times. Then, he made another, and another. By the summer of 1609, he had a telescope that magnified roughly 20 times. He presented this to the Venetian Senate, who were, as the Dutch authorities had been, immediately transfixed by its military potential. From the top of the Campanile in Venice, Galileo demonstrated that ships 2 hours away by conventional sight could be seen clearly through his glass. The Senate doubled his salary and gave him a lifetime appointment at the University of Padua. But Galileo was not primarily interested in ships. He was interested in the sky. On the night of November 30th, 1609, a night we should perhaps observe each year with a kind of quiet reverence, Galileo pointed his telescope at the moon, and everything changed. The moon, as observed by the naked eye, is a beautiful and slightly mysterious disk. You can see, if you look carefully, that parts of it are lighter and parts darker. Ancient peoples saw in these contrasts the shapes of figures, a hare, a man, a woman reading. They called the dark regions Maria, seas, though no one who named them believed they contained water. But through Galileo's telescope, the moon was not smooth. It was not the perfect, crystalline celestial sphere that Aristotelian philosophy demanded all heavenly bodies must be. It was rugged, mountainous, scarred. Galileo saw craters, vast circular formations with raised rims, casting deep shadows in the low-angled light near the terminator, the line between the lit and unlit portions of the lunar disk. He saw mountain ranges. He measured the height of the lunar mountains by observing how their peaks caught the sunlight, while the valleys around them were still in shadow, using geometry, triangulation, the tools of the mathematician, and calculated that some peaks were over 4 miles high. The moon was a world, not a lamp, not a crystal sphere, not a perfect divine ornament hanging in the heavens. A world, with valleys and mountains and plains and ancient scars. And if the moon was a world, then perhaps other worlds too had stories written in their surfaces that human eyes had never read. Galileo kept observing, night after night through that cold Italian winter. On the 7th of January 1610, he turned his telescope to Jupiter, the brilliant, steady point of light in the south that had been observed by human eyes since the beginning of human memory. He saw something unexpected. There were 3 small bright points near Jupiter, arranged in a line. He noted them, somewhat puzzled, and moved on. The next night, they were in different positions, and the night after that, different again. Over the following weeks, Galileo watched and measured and thought. He was watching 4 small bodies. He eventually identified 4 of them, orbiting Jupiter. 4 moons, circling a planet that was not the Earth. This was, quietly, philosophically, profoundly, one of the most devastating observations in the history of science, because it meant that not everything in the sky orbited the Earth. Here were 4 celestial bodies, unambiguously, orbiting something else entirely, orbiting Jupiter, carrying on their steady, indifferent, independent circles, entirely unimpressed by the supposed centrality of our world. Galileo named the 4 moons the Medicean stars, in honor of his patron Cosimo de' Medici, the Grand Duke of Tuscany. Today we call them the Galilean moons, Io, Europa, Ganymede, and Callisto. Europa, the second closest, has, we now know, an ocean of liquid water beneath its icy crust, an ocean larger than all of Earth's oceans combined, an ocean in which, some believe, something may be swimming. Galileo could not have known this. He saw 4 points of light moving around a 5th, but in those 4 moving points of light, the architecture of a heliocentric solar system became visible, demonstrable, undeniable. He also observed Venus and saw that it went through phases, like our moon, waxing and waning from crescent to full and back again. This could only be explained if Venus was orbiting the Sun, moving alternately toward and away from us, with different portions of its sunlit face turned in our direction. He looked at the Milky Way, that soft, smeared ribbon of brightness that had puzzled human observers since the first human looked up. And through his telescope, the Milky Way resolved. The blur separated into stars, thousands of individual stars, too faint and too closely packed for the naked eye to distinguish, but each one distinct and separate and real when seen through the glass. The Milky Way was not a cloud or a river or a reflection of anything terrestrial. It was stars, more stars than the eye alone could comprehend. Galileo published his observations in a small book in March of 1610, just months after his first lunar observations. He called it Sidereus Nuncius, the Starry Messenger. It ran to 60 pages. It sold out immediately. It was translated and reprinted across Europe. It was, without exaggeration, a turning point in human history. And all of it came from a tube of about 1 meter in length, with a lens at each end, built by a professor in Padua who had heard a rumor about a Dutch invention and stayed up late grinding glass. Let your mind rest now, simply receiving the words like rainfall on still water. While Galileo was in Padua, reshaping humanity's understanding of the cosmos, another brilliant and very different mind was at work in Prague. Johannes Kepler was in many ways Galileo's opposite. Where Galileo was confident, polished, politically astute, and sometimes difficult, Kepler was humble, often ill, financially precarious, and profoundly mystical. He saw the universe as a kind of music, as a vast harmonious composition in which the orbits of the planets were the singing voices. But he was also an incomparable mathematician. He had already, by 1609, worked out his first 2 laws of planetary motion, demonstrating that planets orbit the Sun not in perfect circles but in ellipses, and that they move faster when they are closer to the Sun and slower when farther away. When Kepler received his copy of Galileo's starry messenger, he was gripped with excitement. He wrote a passionate, enthusiastic reply, a conversation with the starry messenger, endorsing Galileo's findings and urging the world to take them seriously. But Kepler was also thinking about the telescope itself, about how it worked, about the geometry of lenses and light. In 1611, Kepler published a work called Dioptris, a brilliant, systematic treatment of the optics of lenses. In it, he described something remarkable, a different design for the telescope. Galileo's telescope, following the Dutch design, used a convex objective lens and a concave eyepiece. This produced an image that was right side up, which was convenient for looking at earthly objects, but the field of view was very narrow, and it was difficult to use effectively at high magnifications. Kepler proposed replacing the concave eyepiece with a second convex lens. The resulting image would be upside down, which mattered less for astronomy than for birdwatching. But the field of view would be much wider, and higher magnifications would be far more practical. Kepler himself never built this telescope. He lacked the funds and the instrument-making skills, but others did. And within decades, the Keplerian design had become the standard for astronomical use. It is worth pausing here, in the soft quiet of this late night, to appreciate what Kepler also imagined beyond the practical. In 1608, just before any of these telescopic discoveries, Kepler wrote a story, a fictional narrative called Somnium, which means simply dream. In it, a young man named Duracotus falls asleep and dreams of being carried to the moon, where he observes the Earth moving in the lunar sky and watches the astronomical phenomena of that world. Somnium is often considered the first work of genuine science fiction. But it is something else too. It is Kepler imagining, with the full force of his mathematical mind, what the universe looks like from somewhere other than the Earth. It is the telescope as philosophy, as a mental instrument for leaving the ground, for adopting a different perspective, for understanding that there is no uniquely privileged view of the cosmos. We are all observers. We are all limited by where we stand, and every advancement in the telescope is, in its deepest sense, an attempt to transcend that limitation, to see from somewhere else, to borrow a viewpoint that nature, alone, would never have given us. The decades after Galileo and Kepler were a time of patient, systematic improvement. Let that word settle over you. Patient. Slow and patient. The 17th century was an age of correspondence and collaboration, of letters carried by horse and ship across thousands of miles, carrying not goods or gossip, but ideas. The natural philosophers of Europe wrote to each other incessantly, sharing observations, debating methods, proposing improvements. The central challenge facing telescope makers in the mid-17th century was a phenomenon called chromatic aberration. When light passes through a lens, different wavelengths, different colors, bend by slightly different amounts. Red light bends least, violet light bends most. This meant that a single lens could not bring all colors to focus at exactly the same point. The result was a faint, colored fringe around bright objects, a blurring rainbow halo that softened and confused the image, especially at high magnifications. The solution that many telescope makers adopted was elegant in its simplicity, if rather impractical in its execution. Make the lens very large in diameter and very, very long in focal length. A lens with a very long focal length bends light much more gently, and the chromatic aberration is proportionally reduced. This led to the age of the aerial telescope, instruments of almost surreal length, mounted not in rigid tubes, but as bare, freestanding lenses on long poles. the eyepiece dangling at the end of a rope, swung into alignment with the objective by the astronomer working below. Imagine an astronomer in a dark garden in the Netherlands or Paris or Rome on a cold, clear night, looking up through an instrument that extends 10, 20, 30, 40, in some cases over 60 meters above them, adjusting by feel and experience, waiting for the air to stop shimmering, waiting for that brief, perfect moment of clarity. It was a practice that demanded extraordinary patience and a deep, almost meditative tolerance for discomfort and frustration. Christian Huygens was among the greatest telescope makers and observers of the 17th century. He ground his own lenses, with his brother Constantin, to a quality that surpassed almost everything available elsewhere in Europe. In 1655, using a telescope of his own construction, Huygens discovered Titan, the largest moon of Saturn, a body so large that it is bigger than the planet Mercury. Titan, we now know, has a thick nitrogen atmosphere, lakes of liquid methane on its surface, and organic chemistry of staggering complexity. Huygens saw it as a faint point of light circling a pale planet. It was enough. He also solved one of the great visual puzzles that Galileo had inadvertently created. Galileo, in 1610, had noticed that Saturn appeared to have strange appendages, odd bulges on either side of the disk, that seemed, bizarrely, to sometimes vanish. Galileo was mystified. He wrote that Saturn appeared to be accompanied by two companions, then later described it as having ears. Then, in 1612, when the appendages disappeared, wrote with evident distress that Saturn had swallowed its children. Huygens, with his better telescope, resolved the mystery in 1659. The appendages were a ring, a flat, thin ring of material surrounding the planet, tilted relative to the plane of the solar system, and presenting different faces toward Earth as both Saturn and Earth moved in their orbits around the Sun. When the ring is edge-on to us, it nearly disappears. When tilted, it blazes. Saturn's rings. One of the most beautiful things in the solar system, and one of the most astonishing early rewards of the improving telescope. Around the same time, the Danish astronomer Ole Irmer achieved something remarkable using telescopes and the moons of Jupiter that Galileo had discovered. Irmer was observing the regular eclipses of Io, Galileo's innermost Jovian moon, as it passed in and out of Jupiter's shadow. The eclipses were predictable, regular, clockwork reliable. They should have occurred at perfectly consistent intervals. But Irmer noticed something strange. The eclipses were slightly early when Earth was moving toward Jupiter in its orbit, and slightly late when Earth was moving away. He reasoned, correctly, magnificently, that this was because light takes time to travel. When Earth is moving toward Jupiter, the light from Io's eclipses has a shorter distance to travel, so it arrives a little early. When Earth is moving away, the light has further to go, so it arrives a little late. In 1676, Irmer announced that light travels at a finite speed. He estimated it would take approximately 22 minutes for light to cross the diameter of Earth's orbit. The modern value is about 16 minutes 40 seconds, so he was reasonably close given his available data. For the first time, using a telescope and Jupiter's moons, a human being had measured the travel time of light. The actual velocity in miles or kilometers per second would only be calculated a few years later, when Christian Huygens took Irmer's timing data and applied the best available estimate of the solar system's size. But the great conceptual victory was Irmer's. Light was not instantaneous. It moved, and its movement could be measured. Think of that as you rest. The speed of light, measured in the 17th century, using the shadows of a moon of Jupiter, and the careful attention of a Danish astronomer who noticed something was slightly wrong with his timing. Your breathing is slow and easy now, each breath a gentle tide, in and out. And in, The problem of chromatic aberration, those colored fringes that blurred the edges of celestial objects, was not going to be solved by making lenses longer. The lenses could be made longer, and longer still, but the problem would never fully disappear. The colors would never perfectly converge. Someone needed to think differently. Isaac Newton, in the 1660s, was thinking about everything. He was thinking about gravity, and motion, and the tides, and the colors of sunlight, and the nature of space and time, and mathematical methods for describing curves and changes. He was perhaps the most astonishing concentrated intellect in recorded history, a man who, largely alone, during 2 years when Cambridge University was closed because of plague, worked out the foundations of mechanics, calculus, and optics. On the problem of chromatic aberration, Newton arrived at a conclusion that was, in hindsight, brilliantly logical. The problem with lenses, he understood, was that they refracted light, bent it as it passed through the glass, and different colors bent by different amounts. This was unavoidable as long as you were passing light through glass at all. But what if you didn't pass the light through glass? What if instead of refracting the light, you reflected it? When light bounces off a mirror, all colors reflect at exactly the same angle. There is no separation of wavelength. There is no chromatic aberration. The idea of a reflecting telescope, using a curved mirror to gather and focus light rather than a lens, had been proposed before Newton. James Gregory, a Scottish mathematician, had described such a design in 1663. But Newton was the first to actually build a working one. In 1668, Newton hand-ground a small concave mirror from a metal alloy he had himself developed, a blend of tin and copper called speculum metal, and mounted it in a small tube with a flat secondary mirror to divert the focused light out of the side of the tube to an eyepiece. His first reflecting telescope was tiny, barely 15 centimeters long, but its resolving power equaled that of a conventional refractor 2.5 feet long. He presented it to the Royal Society of London in 1671, and they were astonished. The reflecting telescope solved chromatic aberration entirely, and it had another advantage. Mirrors can be made much larger than lenses. A lens of great size sags under its own weight, distorting its carefully ground curvature. A mirror can be supported from behind, across its entire surface, without affecting the quality of the reflection. This matters enormously, because the fundamental task of a telescope, its most essential capability, is not magnification. It is light collection. The wider the mirror or lens, the more light it can gather from faint, distant objects. Magnification without light collection just gives you a large, blurry image of something still too dim to see. But a large mirror, gathering more photons from a distant galaxy or a faint star, makes the invisible visible. Newton's reflecting telescope set astronomy on a path toward ever larger mirrors, a path that 3.5 centuries later has led us to instruments with mirrors 30 meters across, gathering light from the earliest moments of the universe. We are deep in the 18th century now, the age of enlightenment, a time of exploration and classification and the confident, systematic examination of the natural world. Let your thoughts drift peacefully as we move to England, to the city of Bath, where a German-born musician and his younger sister are about to change everything once again. William Herschel was born in Hanover in 1738, the son of a military musician. He came to England in his 20s, established himself first as an oboist and then as an organist, composer and conductor, and settled in Bath, where he gave music lessons, led the orchestra at the Octagon Chapel, and wrote symphonies and concertos that were genuinely well regarded. But music was not enough for William Herschel's restless mind. In his 30s, he became obsessed with astronomy And like Galileo before him, he decided the best instruments were the ones he made himself. He ground mirrors, hundreds of mirrors. He worked on them obsessively, sometimes for hours at a stretch without stopping. His hands raw, his concentration absolute. His sister Caroline, who had come from Hanover to keep house for him, took over more and more of his domestic responsibilities, and then, increasingly, became his astronomical assistant, his record keeper, and eventually a distinguished astronomer in her own right. On the night of March 13, 1781, William Herschel was conducting his systematic survey of the sky from the garden of his house in Bath. He had built a telescope with a mirror just over 6 inches in diameter, a fine instrument. He was working through Gemini when he noticed an object that didn't look quite right. Rather than the sharp pinpoint of a star, it appeared slightly extended, slightly fuzzy. He noted it as a possible comet and moved on. He returned to it, measured its position, returned again, measured again. It was moving, slowly but unmistakably, against the background of stars. It was moving. But as more observations were made, by Herschel and by other astronomers across Europe who took up the chase, it became clear that this object was not moving on the kind of elongated elliptical path a comet follows. Its orbit was nearly circular. It was a planet, a new planet, orbiting the Sun beyond Saturn, at nearly twice Saturn's distance. The first planet discovered in recorded human history. We call it Uranus, though Herschel's preferred name, diplomatically if somewhat fawningly, was Georgium Sidus, George's star, in honor of King George III. The discovery made Herschel famous overnight. The king appointed him court astronomer. He was given a salary and a house near Windsor Castle, and he used this new security to build ever larger telescopes. His largest, completed in 1789, was for a time the largest telescope in the world. A reflecting telescope with a mirror 1.2 meters, nearly 4 feet, in diameter, and a tube nearly 12 meters long. It stood in the grounds of his house at Slough, like a small industrial structure, a wooden scaffolding climbing alongside it to carry observers to the eyepiece. With this instrument, Herschel catalogued thousands of objects, nebulae, fuzzy patches of light that he believed might be distant collections of stars, perhaps entire universes far beyond our own Milky Way, and double stars, pairs of stars that orbit each other in gravitational embrace. He argued, correctly, that the Milky Way was a flattened disk of stars, and that our Sun was located somewhere within it. He tried to map its structure by counting stars in different directions, a laborious, beautiful, ultimately somewhat inaccurate exercise, because he did not yet know that interstellar dust obscures our view in certain directions. But the conception was right. The Milky Way was a disk. Our Sun was one star among hundreds of millions. Caroline Herschel, working alongside her brother, and then increasingly on her own, discovered 8 comets. 8. In an era when comets were the great prizes of observational astronomy, she found 8 of them, a staggering achievement. Though history records that the first woman to discover a comet was the German astronomer Maria Margaretha Kirch, who independently identified the great comet of 1702, nearly 50 years before Caroline Herschel was even born. Caroline's legacy, however, stands magnificently on its own terms. She also independently discovered several nebulae and star clusters, and she produced a revised and corrected edition of the star catalogue of John Flamsteed, adding over 500 stars that Flamsteed had observed but not catalogued. She was awarded the Gold Medal of the Royal Astronomical Society, the first woman to receive it. She was 78 years old at the time. The Herschels, brother and sister, working through cold English nights with handmade instruments, with careful records kept by candlelight, with aching arms and tired eyes, pushed the telescope to new extremes and pushed human knowledge of the universe to dimensions it had never before reached. The warmth of your bed, the softness of the pillow beneath your head, let each breath carry you just a little further from wakefulness. While reflecting telescopes grew ever larger, the science of lens making was also advancing. Slowly, quietly, in workshops where craftsmen spent their working lives perfecting the art of grinding glass to curves of almost unimaginable precision. The chromatic aberration that had plagued early refractors was significantly reduced in the late 18th century by a development that had taken more than a century to achieve: the achromatic lens. Chester Moore Hall, an English lawyer and amateur scientist, discovered in the 1730s that by combining two types of glass with different refractive properties, crown glass and flint glass, into a compound lens, the different colors could be brought much closer to the same focus. The key insight was that different types of glass have different dispersive powers. They separate the colors of light by different amounts. By combining a converging crown glass element with a diverging flint glass element of the appropriate curvature, the color spreading effect of one could largely cancel the color spreading effect of the other, while the net effect on focusing, on bringing light to a point, was preserved. John Dolland, a London optician, independently developed the achromatic lens around 1758 and was granted a patent for it. The patent was controversial. Hall had the idea earlier, but Dolland was the one who brought it to widespread commercial production. Achromatic refractors were sharper, cleaner, and more useful than their predecessors. As the 19th century began, great refracting telescopes, with objective lenses of ever-increasing diameter, became the prestige instruments of the major observatories. Joseph von Fraunhofer was a Bavarian glassmaker and optical scientist of extraordinary genius. He developed new techniques for producing optical glass of unprecedented purity and uniformity, and he built refractors of remarkable quality for observatories across Europe. But his greatest discovery came not from looking through a telescope, but from examining sunlight through a prism. When you pass white light through a prism, it separates into a rainbow, the familiar spectrum from red to violet. Fraunhofer examined this solar spectrum carefully, using a very narrow slit to sharpen the light before it entered the prism. He systematically mapped something that had been glimpsed before, but never truly understood. The spectrum was not a smooth, continuous rainbow. It was crossed by hundreds of dark lines, narrow, sharply defined gaps where specific colors were simply absent. An English chemist named William Hyde Wollaston had noticed a few of these lines back in 1802, but had not pursued them. Fraunhofer independently rediscovered them in 1814, catalogued over 500 of them, and made them his life's work. He assigned letters to the most prominent ones. We still call them Fraunhofer lines. At the time, their meaning was unclear. Fraunhofer noted that the lines in the solar spectrum matched lines he saw in the spectra of other bright stars. He suspected, correctly, that they were somehow fundamental to the nature of the light source, not artifacts of his equipment. It would take another 50 years for the full significance to be understood. In the 1850s, the German physicist Gustav Kirchhoff and the chemist Robert Bunsen, of Bunsen-Burner fame, worked out the explanation. Each chemical element, when heated, emits light of specific, characteristic wavelength, and each element also absorbs light at those same specific wavelengths when light passes through a cool gas containing that element. The dark lines in the solar spectrum were absorption lines. As the sun's light passed through the cooler outer layers of the solar atmosphere, specific elements in that atmosphere were absorbing specific colors. By looking at which lines appeared and where, by reading the dark lines in the spectrum of a star's light, you could determine what elements that star was made of, from a distance of millions of miles. using only the light that traveled across the void. Spectroscopy, the analysis of spectra, became, almost overnight, astronomy's most powerful tool. Now astronomers were not just measuring positions and brightnesses. They were reading the chemical compositions of stars. They were determining stellar temperatures. They were measuring the motions of stars by the Doppler shift of their spectral lines, the same principle that makes an ambulance siren pitch higher as it approaches and lower as it recedes, but applied to light rather than sound. The telescope had become not just an eye, but a laboratory. We are in Ireland now, County Offaly, a damp and quiet landscape of bog and low hills and ancient stone walls. At Birr Castle, the ancestral home of the Earls of Rosse, an extraordinary project was underway. William Parsons, the third Earl of Rosse, was an aristocrat with a passion for engineering and astronomy. In the 1840s, he undertook the construction of a telescope that would hold the title of the world's largest for over 70 years. The mirror of this telescope was 72 inches, 6 feet, in diameter. Made of speculum metal, it weighed nearly 4 tons. The tube that housed it was nearly 17 meters long. The whole structure was supported between 2 massive stone walls like a ship's cannon mounted between castle ramparts, and it could only swing north and south within a narrow band of sky. It had no freedom to track objects across the whole sky, but could observe anything that passed through the narrow strip directly overhead. The people of the local countryside called it the Leviathan of Parsonstown. With this instrument, Lord Rosse and his observers began, patiently, to examine those fuzzy patches of light that Herschel had called nebulae. Were they clouds of gas? Were they distant systems of stars? Were they, as some speculated, entire island universes, Milky Ways of their own, at unimaginable distances? In 1845, Lord Rosse turned the Leviathan on a nebula catalogued as Messier 51. And he saw something that made him reach for his pencil with trembling excitement. Spiral structure. The nebula was arranged in a great sweeping spiral, arms of stars and light curling outward from a bright center, like water swirling around a drain, like cream folded into coffee. He sketched it. He showed his sketch to other astronomers. They were astounded. We call it now the Whirlpool Galaxy. It lies about 23 million light-years away. It is a spiral galaxy, like our own Milky Way, and Lord Rosse's sketch of it, made with an imperfect eye and an imperfect mirror on a cold Irish night in 1845, is one of the most beautiful and significant drawings in the history of science. The question of what the spiral nebulae actually were, gas clouds or distant galaxies, would not be answered for another 80 years. The answer, when it came, would once again require a better telescope. The darkness behind your eyelids is soft and deep. Like the sky between the stars, there is a quality to the history of the telescope that I find deeply soothing, in a way that is hard to explain. Perhaps it is the slowness of it, the way each discovery built on the one before, not in sudden leaps, but in patient, deliberate increments. Perhaps it is the dedication of the people involved, the long nights, the cold hands, the careful notebooks. Or perhaps it is simply that the story is about light, about gathering light, about not being satisfied with darkness. The second half of the 19th century saw the telescope joined by a new and transformative partner, photography. The human eye, looking through a telescope eyepiece, can only record what it sees in the moment of looking. It cannot accumulate light. A star that is too faint to trigger the eye's light-sensitive cells simply remains invisible, no matter how long you stare. But a photographic plate can accumulate light, keep the shutter open, or in the astronomical context, keep the telescope tracking the object across the sky while the plate is exposed, and the light slowly, gradually builds up an image of objects far too faint for any human eye. The first successful astronomical photograph was a daguerreotype of the Moon taken by John William Draper in 1840. It was blurry and imperfect, but it was real. The face of the Moon, captured on a silver plate, a document that could be examined, measured, compared. Over the following decades, photographic techniques improved rapidly. By the 1880s, astronomical photography was reaching depths that no human eye could match. Nebulae revealed new structure. Star clusters resolved into individual members. Faint comets and asteroids were discovered by the simple technique of comparing photographs taken on different nights. Anything that had moved was not a star. And spectroscopy combined with photography opened a door that no one had imagined before. William Huggins, an English amateur astronomer working at his private observatory in Tulse Hill in South London, attached a spectroscope to his telescope and began examining the spectra of nebulae in the 1860s. For the spiral nebulae, he found a continuous spectrum, suggesting they were made of stars, too faint to be individually resolved, their combined starlight blending into a smooth rainbow. But for some other nebulae, the ring-shaped and irregular ones, he found something entirely different. Not a continuous spectrum, but just a few bright emission lines, the signature of a glowing gas. This meant there were two types of nebula. Some were clouds of gas, genuinely, and others were something else entirely. The distinction was crucial. The gaseous nebulae were local features of our own galaxy. The spiral nebulae, with their continuous stellar spectra, were candidates for being something far greater. But the definitive answer still required a better telescope. We are now in the early decades of the 20th century, and astronomy is about to do something it has never done before in its entire history. It is about to stop using light. Light, visible light, is what your eyes can see. It occupies a narrow band of the electromagnetic spectrum, wavelengths between roughly 380 and 700 nanometers. But the electromagnetic spectrum is vast. It extends from radio waves, with wavelengths measured in meters or even kilometers, through microwaves, through infrared, through visible light, through ultraviolet, through X-rays, through gamma rays, with wavelengths measured in fractions of a nanometer. The universe emits electromagnetic radiation across this entire vast range. But until the 20th century, we had instruments to detect only the thin sliver of visible light. The first radio signals from the cosmos were detected by accident. Carl Jansky was a young engineer working for Bell Telephone Laboratories in 1931. His job was to investigate sources of radio interference that was disrupting transatlantic telephone communications. He built a large rotating antenna. It was called a merry-go-round because it sat on wheels from a Model T Ford and could be slowly rotated to point in different directions, and he set about systematically identifying the sources of static. He found what he expected: interference from nearby and distant thunderstorms, and from other local sources. But there was a third source of radio static that puzzled him. It rose and set on a cycle of almost, but not quite, 24 hours. It peaked every 23 hours and 56 minutes. That interval of 23 hours and 56 minutes is a sidereal day, the time it takes the Earth to rotate once relative to the stars, rather than relative to the Sun. The 4-minute difference accumulates over a year to account for the fact that the Earth is also orbiting the Sun, so the Sun appears to move slightly eastward against the stars from one day to the next. Something on a sidereal cycle was in the stars, literally. Jansky determined that the source was the center of our own Milky Way galaxy, in the direction of the constellation Sagittarius. The heart of the galaxy, a region completely invisible in ordinary optical light because of the thick clouds of dust and gas that lie between us and it, was broadcasting in radio wave. He published his finding in 1932 and 1933. The astronomical community was, at first, largely unmoved. But one person heard it and was captivated. Grote Reber was a radio engineer and an amateur astronomer from Wheaton, Illinois. In 1937, entirely at his own expense and largely with his own hands, he built a parabolic radio dish in his backyard, 9.4 meters across. The neighbors must have found it extraordinary. With this homemade instrument, Reber spent years systematically mapping the radio sky. He confirmed Jansky's discovery of radio emission from the galactic center. He mapped radio emissions from the Milky Way across the whole sky. He published his radio maps in the Astrophysical Journal in 1944. After the Second World War, during which radar technology had advanced tremendously, radio astronomy expanded with astonishing speed. Physicists who had spent the war developing radar antennas and receivers turned their skills to the sky. Radio telescopes sprouted across the countryside of England, Australia, the Netherlands, the United States. The Great Lovell Telescope at Jodrell Bank in Cheshire, England, its dish 76 meters across, still one of the largest steerable radio telescopes in the world, was completed in 1957, just in time to track Sputnik, the first artificial satellite. Radio astronomy revealed a universe invisible to optical telescopes, a cosmos where pulsars, the spinning remnants of collapsed stars, swept beams of radio energy across space like cosmic lighthouses, where quasars, unimaginably bright sources at the edges of the observable universe, blazed in the radio sky, and where the remnant glow of the Big Bang itself, the cosmic microwave background radiation, filled the entire sky with a whisper of ancient, cooled light, first detected accidentally in 1965 by Arno Penzias and Robert Wilson, using a horn antenna designed for satellite communications. They noticed an annoying hiss in their receiver that they couldn't account for. They checked their equipment. They even, famously, cleaned a buildup of pigeon droppings from inside the horn. Suspecting that might somehow be responsible, the hiss remained. It was the echo of the creation of the universe. You are drifting beautifully now, the story flowing around you like the current of a slow, deep river, carrying you gently. In the late 19th and early 20th century, the great mountaintop observatories of America were rising. George Ellery Hale was a solar astronomer, and, more importantly for the history of the telescope, an extraordinarily effective fundraiser and organizer. He was the guiding force behind not one but 4 successive telescopes, each of which was, at the time of its completion, the largest in the world. The Yerkes Observatory refractor, completed in 1897 near Chicago, with an objective lens 40 inches in diameter, is still the largest refracting telescope ever built. Lenses cannot be made much larger, because glass is heavy and sags under its own weight, distorting the carefully ground surface. Hale then turned to reflecting telescopes. The 60-inch Hale reflector at Mount Wilson in California was completed in 1908. The 100-inch Hooker telescope, also at Mount Wilson, was completed in 1917. And it would be on this telescope, on the nights of October 5th and 6th, 1923, that Edwin Hubble would make the discovery that definitively answered the question Lord Rosse had raised with his spiral sketch of 1845. Hubble was examining photographic plates of the Andromeda Nebula, one of the largest and most prominent spiral nebulae in the sky, visible to the naked eye as a faint smudge in autumn nights in the northern hemisphere. He found a Cepheid variable star. Cepheid variables are stars that pulsate in brightness in a regular cycle. A decade earlier, Henrietta Swan Leavitt, working at the Harvard College Observatory, initially as a computer, one of the women hired to analyze photographic plates at a fraction of the salary paid to men, had discovered that the period of a Cepheid's pulsation is related to its absolute brightness. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. Measure the period. You know the true brightness. Compare the true brightness to the apparent brightness as seen from Earth. You can calculate the distance. Leavitt had given astronomers a cosmic measuring tape. Hubble used it. The Cepheid in the Andromeda Nebula was far, far too faint for its pulsation period. The only way to explain the discrepancy was if the Andromeda Nebula was not inside our own Milky Way, but fantastically far away from it. Hubble's original calculation placed Andromeda at roughly 900,000 light-years from Earth. Even that figure, later shown to be a significant underestimate, was enough to place the spiral nebula unambiguously beyond the edge of our own Milky Way. The true distance would only be established in the 1950s, when the astronomer Walter Baade realized that two distinct populations of Cepheid variable stars had been mistakenly treated as one, each with different intrinsic brightnesses. Correcting for this pushed the accepted distance to approximately 2.5 million light-years, the figure we use today, 2.5 million light-years. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. Andromeda is 2.5 million times that distance away. The Andromeda Nebula was not a nebula at all. It was a galaxy. A system of stars comparable to our own Milky Way, containing, we now know, approximately 1 trillion stars, floating through space at a distance so vast that the light now reaching our eyes left its source long before our own species had yet walked the Earth. The universe, that night in 1923, grew beyond anything humanity had previously imagined, and it kept growing. In 1929, Hubble published measurements showing that the other galaxies, 24 of them, scattered across the sky, were all, with a few local exceptions, moving away from us. And the further away they were, the faster they were receding. The universe was expanding. If you ran the expansion backward in time, like a film in reverse, all the matter and energy in the universe converged, collapsed, condensed to a state of unimaginable density and temperature. And then space itself began to expand. Not an explosion in space, not matter hurling outward into some pre-existing void, but space expanding everywhere at once, carrying everything within it along for the ride. What we call the Big Bang. All of this, the expanding universe, the Big Bang. The billions of galaxies, each containing hundreds of billions of stars, revealed by a reflector with a 100-inch mirror on a mountaintop in California. You are getting very sleepy now, very comfortable. Let the words carry you. Earth's atmosphere is a wonder. It protects us from harmful radiation. It keeps us warm. It gives us air to breathe and weather and the blue sky and the colors of sunset. But for astronomers, the atmosphere is also a frustration. Air is turbulent. It moves in eddies and currents, constantly shifting, constantly refracting starlight by tiny, changing amounts. This is what makes stars twinkle. That shimmer is beautiful to the naked eye, but through a telescope it blurs and dances, preventing the sharpest possible images. The atmosphere also absorbs most wavelengths of electromagnetic radiation. Infrared light from warm objects in space is largely absorbed by water vapor before it reaches the ground. Ultraviolet, X-rays and gamma rays are blocked almost entirely, fortunately from a biological standpoint, but frustratingly from an astronomical one. The solution was obvious. If daunting, put the telescope in space. The idea was proposed formally by the astronomer Lyman Spitzer in 1946, before artificial satellites even existed, before the space age had begun. He imagined a large telescope above the atmosphere, able to see with perfect clarity across all wavelengths. The practical realization of that dream took 4 decades of planning, engineering, budget battles, and extraordinary human effort. On April 24, 1990, the Space Shuttle Discovery carried into low Earth orbit a cylinder just over 13 meters long and 4.2 meters in diameter, weighing about 11 tons. Inside it was a mirror 2.4 meters across, smaller than the great ground-based reflectors, but in the purest darkness above the atmosphere. This was the Hubble Space Telescope. The first images from Hubble were disappointing. There was a flaw, a subtle but catastrophic error in the grinding of the primary mirror, a deviation of just 2.2 micrometers from the prescribed shape. 2 micrometers, the thickness of a red blood cell. And yet this tiny imperfection, this almost invisible mistake, meant that Hubble's images were blurry. The public was dismayed. Commentators were unkind. Congress was furious. But the engineers and astronomers of NASA were not defeated. They had anticipated the possibility of a need for servicing. Hubble had been designed to be visited and maintained by astronauts. And in December of 1993, the Space Shuttle Endeavour carried a crew of 7 to Hubble for a servicing mission that has since been called one of the most complex and skilled operations in the history of human spaceflight. Over 5 spacewalks across 5 days, the crew installed corrective optics, essentially precisely shaped mirrors that compensated for the flaw in the primary mirror, the way a pair of glasses corrects a person's blurry vision. When the first post-servicing images came back from Hubble in January 1994, the control room at the Space Telescope Science Institute in Baltimore fell quiet, then broke into applause. The images were extraordinary, pin-sharp, miraculous. Over the following decades, the Hubble Space Telescope would become the most productive scientific instrument ever built. Its images would be seen by billions of people, the pillars of creation in the Eagle Nebula, columns of gas and dust where stars are being born, rendered in colors that feel almost beyond nature, the Hubble deep fields. Long exposures of tiny patches of apparently empty sky that resolved into thousands upon thousands of galaxies, each one a Milky Way, packed into a region of sky smaller than a grain of sand held at arm's length. Galaxies as far as the light travel time of 13 billion years. Images from the edge of time. Breathe slowly. There is only this moment, and this story, and the darkness behind your eyes, and the quiet. On the ground, the telescope continued its patient, relentless growth. In the mountains of Hawaii, atop the extinct volcano Mauna Kea, at an altitude of over 4,000 meters, above much of the water vapor in the atmosphere, in conditions of extraordinary clarity, 2 of the world's most powerful telescopes were built in the 1990s. The twin Keck telescopes each have primary mirrors 10 meters in diameter, but these are not single mirrors. They are made of 36 hexagonal segments, each 1.8 meters across, precisely polished and precisely aligned to act as a single surface. Computer-controlled actuators behind each segment continuously adjust the mirror to correct for tiny distortions caused by temperature, gravity, and wind. Adaptive optics, systems that use rapidly deformable mirrors to counteract the blurring effect of atmospheric turbulence in real time, have made ground-based telescopes competitive with, and in some respects superior to, space telescopes for many kinds of observations. The system works like this: a bright star near the target of observation, or a laser beam fired into the upper atmosphere to create an artificial guide star, is monitored by a sensor that measures how the atmosphere is distorting its image many times per second. The mirror surface is then deformed by tiny amounts, in tiny fractions of a second, to correct for these distortions. The result is images of astonishing sharpness. Adaptive optics allows modern large telescopes to see details on the surface of asteroids, to resolve the orbits of stars at the very center of our galaxy, revealing that they orbit an invisible mass millions of times the mass of our Sun. an invisible mass that we now know is a supermassive black hole, called Sagittarius A. It was imaged for the first time in 2022 by the Event Horizon Telescope. Not a single telescope, but a network of radio telescopes spread across the Earth, from Hawaii to the South Pole, all observing simultaneously and then combining their data to create an effective dish as large as the entire planet, an Earth-sized telescope. It had already made history once before, in 2019, when it produced the first image ever taken of a black hole, a glowing amber ring surrounding the supermassive black hole at the heart of the distant galaxy M87. 6.5 billion times the mass of our Sun. That image was seen by virtually every person on Earth with access to a screen. And then, in 2022, came its first image of our own galaxy's center, a glowing ring of hot gas, orange gold against the darkness, with a shadowed interior, the shadow of a black hole, 4 million times the mass of our Sun, at the center of the Milky Way. Hans Lippershey's 3-power spyglass, built in Middelburg in 1608, has become a planet-sized telescope, imaging the shadow of a black hole. The distance from one to the other is almost too great to comprehend. We are very nearly at the present now, at the newest chapter in this ancient story, and perhaps the most extraordinary one of all. On December 25th, 2021, Christmas morning, a rocket launched from a spaceport in the jungles of French Guiana, carrying a telescope folded up like origami inside its fairing. The James Webb Space Telescope had been in development for over 25 years. Its total cost, across design, construction, testing, and launch, was approximately $10 billion. It had survived budget crises, technical challenges, a pandemic, and an almost paralyzing level of public and scientific expectation. It unfolded in space over the course of 2 weeks, a process of 344 individual steps, each of which had to succeed for the telescope to work. A single failure, a single component that stuck or malfunctioned, and the entire mission would be lost. The mirror, a hexagonal mosaic of 18 gold-coated beryllium segments, 6.5 meters across when fully deployed, was the largest mirror ever launched into space. It was coated in a microscopically thin layer of gold, because gold reflects infrared light almost perfectly. James Webb is an infrared telescope. It doesn't see visible light, at least, not primarily. It sees heat. This is not a limitation. It is a superpower. The universe is expanding. Objects far away from us are moving away from us, and as they do, the light they emit is stretched. Its wavelength increases, just as the pitch of a receding ambulance's siren drops. For the most distant objects in the universe, galaxies that formed in the first few 100 million years after the Big Bang, this stretching is so extreme that what was originally visible or ultraviolet light has been stretched all the way into the infrared. If you want to see the first galaxies, the first stars, the first light that followed the darkness of the cosmic dawn, you need to look infrared. The first science images from the James Webb Space Telescope were released in July 2022. They were, and I say this without hyperbole, staggering. In one image, Webb's version of the Hubble Deep Field, thousands of galaxies packed into a tiny patch of sky, each one shining with the light of billions of stars, the most distant of them sending their light to us from a time when the universe was less than 1 billion years old. In another, the Carina Nebula, a great cloud of gas and dust where stars are being born, resolved into columns and cliffs and towers of luminous gas, star-forming peaks rising thousands of light-years high, their surfaces etched by the fierce radiation of newly born stars blazing within them, each one rendered with a clarity and a beauty that made grown scientists weep. And in the spectra of exoplanets, planets orbiting distant suns, Webb read the chemistry of alien skies. In the atmosphere of WASP 96b, a gas giant roughly 1,150 light-years away, it detected clear signatures of water vapor. In the atmosphere of WASP 39b, a different world roughly 700 light-years away, it identified carbon dioxide and sulfur dioxide, the first time carbon dioxide had ever been definitively detected in the atmosphere of a planet beyond our solar system, the first time in history that the chemistry of a world beyond our solar system was directly measured. And this is only the beginning. Webb is expected to operate for at least 20 years. It will examine hundreds of exoplanet atmospheres. It will peer into the early universe with unprecedented depth. It will find things that no one has yet imagined finding. Meanwhile, on the ground, the next generation of giant telescopes is already under construction. The extremely large telescope, being built by the European Southern Observatory on the Cerro Armazones mountain in the Atacama Desert of Chile, will have a primary mirror 39 meters in diameter, larger than a tennis court. When it sees first light, technical first light now expected in 2028 or 2029, with full scientific operations following around 2030, it will be the largest optical telescope ever built. Its adaptive optics system will deliver images 8 times sharper than Hubble's. It will be capable of imaging Earth-sized planets around nearby stars. It may one day, for the first time, take the spectrum of a potentially habitable world and look for the chemical signatures of life: oxygen, methane, ozone, the fingerprints of biology. From a tube of 35 centimeters in Middelburg in 1608 to a 39-meter mirror in the Atacama Desert in the 2020s, listening for the breath of living things on worlds orbiting other suns, we have come a long way tonight. From the campfire in the darkness of a world without cities, to the clay tablets of the Babylonians, their careful hands pressing symbols into wet clay, to Alhazen in his lamplit library, bending light through water and glass and thought, to a workshop in Middelburg, where perhaps a child held 2 lenses up and saw a distant spire leap toward them, to Galileo in his garden in Padua, on a November night, turning a small tube toward the moon and seeing mountains, to Caroline Herschel, cold and awake long past midnight, a comet moving through the eyepiece of her telescope like a secret written in light, to Römer, patient in the observatory at Paris, his careful timings revealing that light is not instantaneous, but travels, as everything travels, through the patient dimension of time, to Hubble, bending over photographic plates in the dark of the developing room, measuring the distance to a galaxy whose light began its journey before our species existed, to engineers and astronauts in December 1993, floating in the void above the atmosphere, making a mirror see clearly, to the engineers and scientists gathered around screens in July 2022, watching the first full-color images from James Webb unfold pixel by pixel across their monitors, some of them laughing, some of them crying, all of them aware that they were seeing something no human eye had seen before, something from the first chapter of the universe. All of this is one continuous thread, one unbroken line of human curiosity, stretching back through every century, every civilization, every cold night, spent outdoors with one's eye pressed to a tube or an eyepiece, or a sighting rod, or simply tilted up toward the stars with nothing between the eye and the sky but wondering. And what is the thread made of? It is made of patience, of attention, of the willingness to look carefully and to record what one sees, and to ask, quietly, persistently, without demanding an immediate answer, what does this mean? It is made of the stubborn, beautiful refusal to be satisfied with not knowing. And here is a thought to carry with you as you drift toward sleep. Every photon of starlight that has ever entered a telescope's lens or mirror, every one of those particles of light, has been traveling since it left its source, sometimes for years, sometimes for thousands of years, sometimes for billions of years. The light from the stars you can see in tonight's sky left those stars long before you were born. Some of it left before the Earth existed. Some of it left before our sun was formed. The universe sends us messages from across time, written in light. And for most of human history, those messages arrived at our eyes and were received, but not read, not fully, not deeply. The telescope is how we learned to read them. It took us over 400 years, and we are only just beginning. Let your body be still now. Let your breathing be slow. Let the images of all those nighttime skies, the campfire skies of our ancestors, the canal-lit skies of Galileo's Italy, the fog-soft skies of Herschel's England, the crystalline dark of a Chilean desert mountaintop, let them drift and blur and mingle like stars dissolving into the Milky Way. Somewhere, right now, a telescope is pointing at the sky. Many telescopes, dozens of observatories on a dozen mountaintops, their domes slowly rotating to follow objects as the Earth turns. Satellites orbiting above the atmosphere, their mirrors drinking in the light of the early universe. Radio dishes arrayed across continents, listening to the slow music of the cosmos. While you sleep, the work goes on. The light comes in. The data is recorded. And somewhere, someday, in a quiet room with coffee growing cold on a cluttered desk, someone will look at a graph, or an image, or a number, and feel that same ancient animal stirring. The one that began by a dying campfire under a sky too full of stars to count. And they will say, something is there. What is it? And the universe, patient and vast and almost impossibly old, will have another secret drawn gently from it. Sleep now, sleep, and dream of open skies, of mountains on the moon, lit silver in the slant of a distant sun, of 4 small points of light, circling a giant planet in the cold of deep space, of a woman in a cold English garden, pencil in hand, a comet moving through her telescope's field of view, of the first photograph of a galaxy, a smear of silver on a glass plate, a trillion stars in the palm of a hand, of gold-coated mirrors unfolding in the darkness above the atmosphere, like a flower opening slowly, deliberately, toward the light of the oldest stars. The universe is 13.8 billion years old. The telescope is over 400 years old. In the life of the cosmos, it is a blink, a flicker. And yet in that blink, our small and curious species has reached from our small and beautiful planet all the way to the edge of time. Not bad. Not bad at all. Good night. Good night.